for International Academy, and besides giving 3 lectures here, he's also going to give a tutorial, and I think he has some homework for you before you do the tutorial, which is the tutorial's tomorrow afternoon, right?
Yeah, actually I might as well pitch it right now. So tomorrow at 5 o'clock, the last lecture of the day tomorrow, was going to be outside of this lecture series. I still think of this more like performance art than anything else, but I will sit down and open a fresh Mathematica notebook, and in about 40 minutes or so have a completely working and internally verified code for all 3 amplitudes in Yang-Mills theory. And those of you who know Mathematica, I hope it'll be instructive, and those of you who don't, I still think it should be instructive and interesting to watch at least. But for the purposes of making sense of that walkthrough tomorrow, that tutorial tomorrow, you should look at the notes that are available on the website. It's just 3 pages. You do not need to understand those notes, but familiarity with them would be helpful, just because I'm going to assume that you know what the recursion relations look like in terms of these variables. The purpose of the exercise is that you're supposed to be approaching this recursion relations from the point of view of somebody who doesn't know exactly, isn't already familiar with everything. So it's okay not to understand those notes, but it'll be helpful if you at least look at them tonight before tomorrow. Okay. So the lecture today, and let me start by just summarizing some of the incredible advances that have taken place in the last few years. We have all-loop recursion relations for an increasingly broad class of quantum field theories. We have nice closed formulas for high loop expressions, which can be generalized to general quantum field theories and to pretty high loop order. In terms of these pictures here that Zvi drew this morning, there's the amplituhedron and its beautiful geometry, and the positive Grassmannian, which some of you have seen these pictures. Some of you wearing t-shirts might have it on it, this picture on it. And one of the important characters in this story, this emerging reformulation and re-understanding of quantum field theory, are pictures like this. These are pictures of something called on-shell diagrams, which I'll define, and this will be mostly the theme of this talk. And it's been known since the early 90s from the point of view of generalized unitarity that if you knew these kinds of functions that I'm going to define, these are the residues of multi-loop amplitudes, and with some qualifications, like for example, maybe you need to know them in d dimensions and not in 4 dimensions. But if you knew this kind of data and you had an integrand basis, you could reconstruct perturbation theory at the level of integrand for any quantum field theory without really any qualifications after that. So what's nice about these functions is that they're built purely in terms of on-shell data, meaning physical data, gauge invariant, redundancy-free data. And that's going to be really the theme of this talk, or of these lectures. And in particular, something that happens that's fairly magical for theories in 4 dimensions with massless particles, which is that these cuts take kind of a nice form, and there exists a beautiful correspondence between this class of objects defined in quantum field theories involving massless particles in 4 dimensions, like, for example, most of the standard model. There exists a correspondence between these pictures and a beautiful geometry inside the Grassmannian. And so this correspondence looks like, I just want to set the stage kind of in a big picture here at the beginning. So this is a picture of one of these kinds of on-shell functions, and you can think about it as some residue of a 4-loop amplitude for 6 particles or something like that. But I think it's defined, we can give it an intrinsic definition from the first principles of locality and unitarity in quantum mechanics, which I'll walk through in just a few slides. But there exists a correspondence between any function like this in 4 dimensions with massless particles and a certain volume of a certain subspace of a Grassmannian manifold. And this might just seem cute, but it actually has a lot of powerful applications in both directions. From this correspondence, the physics has a lot to inform about the geometric structure of these volumes and inside the Grassmannian and how they fit together, and it poses a lot of interesting questions for mathematics, a lot of which are open. There's a lot of low-lying fruit. And from the mathematics, we can learn a lot about the physics. So what this correspondence looks like in more detail, and we're going to flesh out this correspondence over the next few lectures. So for every picture like this that you can draw, corresponds to some function in physics defined in this way that I'll define in more detail in a few minutes. There exists some submanifold of a Grassmannian of k-planes and n dimensions, and I'll define what that is too. But there exists some geometric structure with a volume form that depends a lot on the quantum field theory in question. And from here, volume-preserving diffeomorphisms correspond to physical symmetries of that function. Whether or not they're physical symmetries of an amplitude is a different question. But being subspaces of diffeomorphisms, it's almost certain that these things are infinite dimensional symmetries on general grounds, which is a very interesting observation, that there are infinite dimensional symmetries in four-dimensional quantum field theories, at least in terms of these building blocks. Trivial symmetries by this, trivial is the wrong word, but it really means two-term identities, that f equals f prime. That corresponds to a diffeomorphism, so that's an identity. And in particular, these can be generated by cluster coordinate mutations. And some of you might have heard the words cluster coordinates or clusters. I think there'll be some talks next week on clusters, and Claude Dour will probably talk about them too. They're an extremely rich area of mathematics, and there's a lot of applications to physics, and they make an appearance here as a generator of this infinite dimensional class of identities. Or rather a restriction of the infinite dimensional space of symmetries. But also geometric identities, homological identities inside the right-hand side in the Grassmannian correspond to functional relations on the left-hand side. So it allows you to organize your work in a nice way. So let me just show you what this kind of correspondence looks like. And again, we're going to derive this in much more detail in the course of these lectures. But for planar theory with maximum supersymmetry, of which there's only one, we're talking about two colored, undirected graphs that are drawn on the plane, like this. So any graph like this makes sense. And the strata, I'll show you how to construct this map in the course of these lectures. But you get some submanifold inside the space of k by n matrices. And the volume form is about as simple as it could possibly be. It's just d log, d log, d log, and all the variables. Okay. These things are called positoroid varieties. The volume form is the canonical top form on the positoroid varieties. And it turns out that in this case, for this particular quantum field theory, one of the many reasons why it's our favorite quantum field theory in the amplitudes community, everything turns out to be combinatorial. There's a combinatorial description on the left-hand side of the geometry. Everything is combinatorial. So it allows you to re-express perturbation theory at least in purely combinatorial terms, which is extremely nice. And these infinite dimensional symmetries do survive to amplitudes. And it's called the Yangian. And it was a symmetry that was undiscovered for 30 years since this theory was originally defined at the level of Lagrangian. It went unnoticed for 30 years, and it's a trivial property of these diagrams, and it's kind of easy to see that it's preserved for the amplitudes at least at the integrand level. If you have less supersymmetry, the only thing that changes, the geometry is identical. The graphs are pretty much the same. There's also some labeling for the graphs. But importantly, the difference between a supersymmetric theory and a maximally supersymmetric theory and any less than maximal supersymmetry, including no supersymmetry, is that you have to have oriented graphs. And that changes this function in a slight way that depends on the orientation of the graph. And for this example, like many of them, the prefactor is 1 to some power, which means it doesn't change. This thing is invariant under no matter how much supersymmetry you might have, including none. But we can do this for non-planar theories. Non-planar theories, this is for n equals 4, but the volume form would be slightly different in n equals 8. But still, the geometry is the same in both cases. The volume form depends on the theory. And we can talk about non-supersymmetric, non-planar theories as well, and there's some nice structure there. One of the other things that this correspondence immediately gives you is that as we will see, there is a finite number of essentially different functions that you need to care about to all orders of perturbation theory. That's a big deal. It tells you that at a certain loop order, everything kind of shuts off and you start seeing the same things again. And that's a special thing. But there are some kind of obvious open questions about this correspondence. And it's amazing how simple, how how open these questions really are. So, for example, I just told you that there's a finite number of functions. How many? How do we name them? How do you identify them? What functional relations do they satisfy? What are these infinite dimensional symmetries? And do they have anything to do with amplitudes? Unknown. And it turns out that these functions naturally encode simultaneously functions or distributions, and also integrals over functions and distributions. And it turns out that in the case of planar maximum a natural question to ask is whether or not a loop integrand is inside is spanned by this class of functions. And in the case of planar maximum supersymmetry, in fact planar anything above non-zero supersymmetry, this is true. So there are loop level recursion relations that immediately capture this in terms of that. Okay. Now this is the big picture, and I want you to keep this in the back of your mind as we go ahead. But today, I'm not really going to get to the correspondence. I'm going to spend most of today, in fact, pretty much all of today, on the left-hand side, basically laying the foundations we'll have for building up this correspondence constructively in the next couple lectures. And in particular, I'm going to describe 3 different ways to construct this correspondence from first principles. One, it feels like it's bottom up, the other one's top down, and maybe the last one is inside out or something. But we'll construct this in at least 3 different ways in the course of these lectures. But today I'm going to mostly focus on this and kind of lay the groundwork for why you'd be interested in drawing these kinds of pictures, even outside of the context of unitarity, where you might use them to construct loop integrals. And in the next couple lectures, we will see how this correspondence naturally emerges as just a way. There are several ways in which you would have guessed that. Okay. But I want to start. But this lecture in particular is going to be somewhat broad and somewhat, simple. There should be a considerable amount of overlap with things that you've already seen, or I hope you already know about. And so I hope you don't mind interrupting me with questions as we go along. But I want to start really at the very bottom, which I think is the foundational parable of the Amplitudes program, which is computing scattering amplitudes. I think a lot of developments, whether or not they're directly geared towards simplifying work of calculating things, a lot of them are motivated by the desire, or by trying really hard to compute something that's really hard to compute and finding out that the answer is fairly simple. And there is a classic example that I hope you all already know, but I want to remind you of it here, which is consider the computing the amplitude for 2 gluons to collide and create 4. This happens millions of times a second at the LHC, and it's important. But it's hard. In fact, I think it's safe to say that it would have been intractable before modern computers. And I actually mean that in a very literal sense. Why? It's 220 Feynman diagrams, thousands of terms, and if you tried to approach this from the point of view of most quantum field theory textbooks, you wouldn't even be computing the amplitude, you'd be computing the cross section, you'd be squaring this. You're talking about millions and millions of terms. You're not going to do it on pen and paper. And this was literally considered computationally intractable. There's this paper from 1984 outlining the challenges to be faced by a superconducting supercollider, where they pointed out, so here's the relevant page, they pointed out that the cross sections for 2 to 4 processes have not been calculated, and their complexity is such that they may not be evaluated for the foreseeable future. It is worthwhile to seek estimates of 4-jet cross sections, even if only reliable in restricted regions. Right? They literally viewed this as not only hopeless, but hopeless forever. And yet it's so important for experiments that they wanted somebody to estimate it, and maybe in just restricted regions. Okay? They clearly didn't anticipate the iPhone or something. Yeah.
When was this paper written?
1984, in the context of the superconducting supercollider. Okay. Well, saying that something's impossible is usually a great way to motivate people. And within a few months of this, or knowing about this preprint, 2 physicists at Fermilab took up the challenge, Stephen Park and Thomas Taylor, and they used every trick imaginable. They introduced a fake supersymmetry, an n equals 2 supersymmetry, which is just weird from today's point of view, to trade this into something with a lot of scalars, which is also weird thing to do from today's perspective. But anyway, they introduced some supersymmetry. They used some notation and some ideas that were very, very new, at least to them. And they had one of the world's most powerful supercomputers at their disposal. And they threw it all together, and they got the answer. And as soon as they did, they cleaned it up as much as they could, and they rushed it to publication with such a beautifully concise abstract. The cross-section for 2-gluon to 4-gluon scattering is given in a form suitable for fast numerical calculations. Okay? They clearly had an experimental application in mind here. So the formula, it was compact. You know, it's hundreds of Feynman diagrams, but they got it down to 8 pages. And the formula looks like this. Everybody should look at this in detail sometime. These are matrices of coefficients to simplify the result. Okay? And there it is. You'll notice that there's almost no words in this paper. It's just a big formula. But the reason why I absolutely love this, so of course, as we always do, they promise to give details in a future paper. They just wanted to give the result. But what makes me just absolutely love this paper is this kind of unusual optimism at the very end. Furthermore, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist's, but also a theorist's delight. Okay, they clearly saw something. And I've had a chance to speak with Stephen Park about this quite a bit. And there's an interesting story there about why they expected to see something simple. But they had some intuition that this was unnecessarily complicated. And sure enough, within 6 months, they stumbled upon a guess that they checked against that 8-page formula. And Stephen claims he still has the tape, presumably, of the original program. But they checked it numerically, that this process, that 8-page formula on the previous page, is equal to that. In notation that Yutin probably explained before, these are, I'm going to review it in a moment anyway, but just this, these in terms of these spinor determinants here, not the notation they used. But much more impressive than just collapsing 8 pages down to one line is that this formula naturally suggested a guess for 2 particles to create any number whatsoever. An all multiplicity formula in one line. So, and if this does not impress you, then you have no soul. I mean, when two gluons create 50 gluons, the number of Feynman diagrams at tree level is 2 times 10 to the 83. It exceeds the number of atoms in the universe. And here it is, just one line. I think this is a sharp indictment on the way we understand and we think about quantum field theory. This simplicity needs to be explained. And it'll be kind of a throwaway application in this lecture today that I will understand, in particular, this simplicity. But I think that understanding this, if enough people had stared at this and thought about it carefully long ago, I think we would have been led to a lot more advancements early on. And so I'm going to try to, well, I'm not going to do a very good job of being careful about the right historical order of events or anything like that in these lectures. But I will try my best to rewrite history in the way that I think it should be rewritten. And so I think from Yutin's lectures, you probably know already that you probably already know this formula. This is called the MHV amplitude. And I phrased it in a certain way. This is 2 particles to create any number of same helicity. So if you reverse the helicity flow on all the outgoing particles, it's the 2 incoming minuses and all the rest incoming pluses. But there are 2 ways that would have led you to the Grassmannian. And the one that we're going to talk about tomorrow, I think, really starts from just trying to generalize that. Imagine trying to calculate 3. Is there a Park-Taylor-like amplitude for 3 particles to create 3 particles, or 3 particles to create some number with the same helicity? The NMHV, or end of the KMHV. And I will leave this as a bit of an exercise, but if you sit down and think about the supersymmetry and which is really just a complicated way of saying little group in this particular case, it's easy to see that this formula minimally requires some generalization into, instead of a 2 by 2 determinant, it needs to be a k by k determinant. And if you start guessing a formula like this, I think you will lead very quickly to a Grassmannian, which we'll see tomorrow morning. But today, I want to lead us to the Grassmannian from a much more kind of naive or simple point of view, which is just how to understand formulas like this, that are this simple. How on earth can we wrap our minds around something like this when it's at such a contentious odds against the Feynman expansion and our intuition from summing Feynman diagrams? And to do that, I think we need to step back a bit and maybe survey the big picture. I think it's clear from that example that the culprit in this, or at least a very likely culprit, is the gauge redundancies, all of the virtual particles, the virtual degrees of freedom, the unobserved degrees of freedom that are part of the Feynman expansion. And all of these things must be canceling out in some way. So it's useful to think back and just talk about what does an amplitude depend on. So an amplitude, I'm going to represent as this gray blob like this. What does it depend on? For the eighth particle, it depends on the particle's momentum, obviously, and its mass, but these two are related. The relativistic version of E equals mc squared tells you that that they satisfy p squared equals m squared. This defines a hyperboloid, and if p satisfies this, we say that it's on the mass shell. That's what on shell means. So by that, I just mean that it's a particle that, or it's a particle that satisfies Einstein's equation, which means it's observable. Okay. Now, of course, there's also the spin and the helicity, which takes a discrete value in 4 dimensions. I should generalize this if I wanted to talk about d dimensions and to talk about little group. But anyway, in 4 dimensions, we're just talking about spin. And for a massless particle, it takes a binary digit. It's either plus or minus the spin of the particle, the helicity. And then there's collectively all of the non-kinematical quantum numbers that describe it. The flavor, the generation of the particle, the color, et cetera, that I'm going to collectively call a color, basically. And I realize that it's a bit at odds with Zvi's lectures, or at least I think there's hope that the color quantum numbers, for example, can be upgraded into a kinematical, that there is actually something, that it is kind of a kinematical variable, but I will leave that to you. For the rest of these lectures, I'm going to basically ignore the non-color, the non-kinematic parameters. Okay, now so we'd think that you open up a textbook on quantum field theory and you find out ways of computing this that depend on s's and h's and p's that satisfy p squared equals m squared, and of course, we all know that's not true. Instead, we open up a textbook and we find there are Lagrangians, there are polarization tensors, and we introduce gauge redundancies. We have too many degrees of freedom for a massless particle, and all of this gets canceled out by Ward identities and by gauge invariance at the end of the day. But it's not really a symmetry, it's a redundancy. And for spin 1, for example, the fact that polarizations are not unique, that they're specified up to an equivalent, that you can at best specify a representative of an equivalence class, is kind of a big problem computationally. And I think that from the modern perspective, it's this kind of unphysical baggage that is almost certainly responsible for the complexities, the unnecessary complexities of the Feynman expansion. Okay. So if we're going to forbid ourselves from talking about gauge redundancies, ghosts, first dual particles, and all that other unphysical baggage, what are we allowed to talk about? Well, clearly we're allowed to talk about amplitudes. An amplitude is clearly a function of observable data. But if we knew any amplitudes whatsoever, we could build them into a broader class of functions. For example, a factorization channel here. And the meaning of this picture, the meaning you might have in the back of your mind is that this is a residue of a tree amplitude or something where you put a propagator on shell. But I don't want to define it that way. I don't want to define these pictures relative to a virtual dependent picture. I want to define them intrinsically, and the intrinsic definition of this thing follows directly from basic principles of quantum mechanics. So this internal particle, I declare that it's on the mass shell. It's a real observable particle. And that means that in a local quantum field theory, this process and this process can be separated by arbitrary distances in space and time. This is a real virtual particle that can move around. And that means that in any local quantum field theory, these two processes must be independent. And so whatever the meaning of this picture is, that it's a product of those two. Okay. Now unitarity dictates that because we don't see the particle either, we have to sum over all the possible particles of I. We have to sum over a complete set of states. And in this case, that actually means an integral. That sum means an integral over the Lorentz invariant phase space for each particle, which in d dimensions is some d minus 1 dimensional integral. And we sum over all the possible states, their helicities, the colors, everything. OK. And that is clearly the meaning of this. And that meaning generalizes immediately to an arbitrary graph of amplitudes connected by any number of internal particles, which I'm going to call an on-shell diagram. And the functional meaning is simply the product of all of the amplitudes integrated over the on-shell phase space of every internal particle.
So are those momenta in the middle always real?
No. No, usually not, actually.
So then the phase space integral, you need to define it a little bit?
Yeah. Yeah, it's going to be a complexified space. Well, it's real in two signature in 4 dimensions, for example, but that's cheating. So it's a little bit odd. I mean, it is, Lance mentions an important point here, which is an oddity of, at least the way I view this, is that I have this strong inclination against taking a particle to be virtual, but I am completely blasé about allowing it to have complex momenta, which is a little bit unusual. Anyway, I think that's justified from, anyway. Just to know, when I say something's on shell, it could be complex on shell. OK, so one of the properties of this kind of graph is, there are many things. We're going to study these diagrams in more detail in the next few lectures. But kind of an order 0 characteristic of any diagram like this is how many constraints are there. So every single amplitude in every vertex has a momentum conserving delta function. So there's at least, the number of delta functions is at least d per vertex. OK? Now every internal line is a phase space integral, which can soak up at most d minus 1 of them for each internal line. So this is how many delta functions there are left over if all of the integrals can soak up all of the delta, as many as they can of the delta functions. But of course, any graph of momentum conserving vertices will conserve momentum across the entire graph. So it's natural to kind of talk about, to remove overall momentum conservation from this. And from this you can see that this thing has n hat delta equal to 1, meaning that there's one delta function beyond overall momentum conservation, which is the obvious one, which is that the p squared of that internal line is equal to the mass squared of that internal line. That is the one constraint for this diagram. So this number counts the number of excess delta functions. It's minus the number of remaining integrations. And if it's 0, for example, a d-gon in d dimensions will always have n hat delta equal to 0. This is just an ordinary rational function. Maybe it's algebraic, but it's usually, depending on how you define it, it's probably rational. And if n hat delta is greater than 0, it has some sort of distributional definition. And if n hat delta is less than 0, there's some number of integrals which the definitions I've given you so far do not define, because I haven't told you how to do this contour of integration or what contour to choose if there isn't a delta function around to completely lock it. So what actual integrals to do might require some further specification if n hat delta is negative. OK. Now to get any further progress, we need to go to 4 dimensions and talk about massless particles in 4 dimensions. And I'm going to go through this kind of quickly, mostly because I understand that Yutin already told you all about this. But I want to just pause here and there just to clarify my notation for the rest of these lectures here. So P, this corresponds to, I can dot them into the Pauli matrices and get a 2 by 2 matrix. We can write this as lambda, lambda tilde in the normal way. When P is real, lambda and lambda tilde are complex conjugates up to a sign. There's the little group, which leaves the momentum invariant, but does not leave invariant wave functions, external wave functions, and therefore on-shell functions scale in a uniform way, depending on the helicity of the particle. And the Lorentz group acts as SL2 left times SL2 right on lambda and lambda tilde respectively, and that means that Lorentz invariants are built out of determinants here. So angle bracket, square bracket, that's my notation. If you like epsilons, that's the formula. OK, and that means that the kinematic data that specifies an amplitude is a pair of 2 by n matrices. Also the helicities, of course. But this pair of 2 by n matrices. And just to get the notation clear, when I write an index, I mean the index. And when I don't, I mean marginalize over all the indices not drawn. So this whole 2 by n matrix is collectively denoted by lambda. And if I cared about the row, the top row, I would write lambda upper 1 and lambda upper 2 for the entire row. And if I just wanted to talk about the columns of this matrix, I'd write a lower 1 through n. So an index that's not drawn, I mean collectively take the rest of the indices. OK, now one other reason besides just defining some notation for reviewing this material is that there's a nice kind of geometric interpretation that's just at this point is just kind of cute. It's an excuse for me to define the Grassmannian for you, which is that because Lorentz transformation act as SL2 left on lambda, for example, and because little group allows you rescaling, the Lorentz invariant content of the kinematics here is the plane, the span of these 2 row vectors in Cn. So what I mean by this is that there's some n vector lambda 1 and there's some another n vector lambda 2. And SL2 allows us to rotate these things into each other. And then the little group allows us to rescale it. So that the Lorentz invariant modulo Lorentz transformations means this 2 by n matrix modulo GL2. And GL2 is the space of 2 by n matrices modulo GL2 is an example of a space called the Grassmannian of 2 planes in n dimensions, which you can always think of as the k plane in n. GKN is the space of the linear span of k n-dimensional vectors. Which you can think about as representing as a k by n matrix, understood that that's a representative of a GLK equivalence class. OK. Now one final thing, and this is just a way for me to introduce one bit of notation that's going to be recurring and possibly confusing, is that so momentum conservation is the sum of all the momenta equals 0, if I take them all to be incoming or outgoing, which of course in this notation becomes the sum of lambda tildes, and which is a 2 by 2 matrix of delta functions. I will always write my a matrix of delta functions. I will indicate the size of the matrix in the numerator, in the exponent there. Anyway, when you sum over the particle index, I'm going to write dot, which is a matrix operation means dot transpose. And I realize that, and I'm sorry about it, but I just can't bring myself to write transpose on every single expression everywhere. And so I'm just when you see a dot, it means sum over particle index. OK. Now this means that momentum conservation has an interesting geometric interpretation here, which is that for every k-plane in n dimensions, there's a natural dual space, which is the space of n minus k-planes that are not spanned by the k-plane. It's the complementary space in n dimensions. And this dual I'm going to write as perp. So not to be confused with transpose. And so momentum conservation tells you that lambda and a lambda tilde are orthogonal. What that really means, I don't mean orthogonal necessarily. What I really mean is that they're in each other's orthogonal complements. So there's some 2 plane in n dimensions called lambda. There's an n minus 2 plane in n dimensions called lambda perp. And lambda tilde has to be spanned by lambda perp. Has to be, a subspace of lambda perp. And vice versa. And I'm going to spare you there's one case basically where this geometric intuition has some interesting value, and that's for 3 particles, where I assume that Yutin already walked you through the derivation of the 3 particle amplitude. So I'm going to go fairly quickly through this just to basically review the notation. So in the 3 particle case, this has an interesting implication, which is that the analytic continuation of the 3 particle S matrix is unique. It's uniquely fixed. Of course, it has to vanish for real momenta, but it has a unique analytic continuation. Considerations of smoothness in the limit of real momenta dictate that if the sum of the helicities is negative, it's a function of just the angle brackets, and if the sum of the helicities is positive, it's just the square brackets. So we have these 2 cases. And in a theory like Yang-Mills, where there's exactly one species of particle, or not species, but one kind of particle up to other quantum labels, and it's CP conjugate, so there's basically one helicity kind of particle, and it's plus or minus, then we can denote the helicity flow by arrows, and we'll talk about oriented graphs. And as I hope Yutin reviewed, the one nice thing about maximum supersymmetry is that all the possible helicity components are encoded by one super function. And so there's a one super function of this type and one super function of that type, and that's really about it, about what's simple about n equals 4 or n equals 8. which is that I don't need to draw arrows in all my graphs. The space of functions just grows by all the ways you can draw arrows on graphs. In fact, it doesn't grow that much, but it grows at most by that much. But this is really what's being bought by talking about maximum supersymmetry. Okay, now given these three particle amplitudes, which again are well defined for any massless theory in 4 dimensions, we can start gluing them together into a wide variety of meaningful gauge invariant on-shell functions that we can define in, we can talk about this in n equals 4, we can talk about this non-planar, we can talk about it in n equals 8, we can talk about it in non-planar QCD, we can talk about it in QED if you'd like. Any theory with massless particles in 4 dimensions, you can describe these functions in terms of these graphs. Okay, and I hope I've convinced you at least, I hope you believe me at least, that this kind of picture, that the meaning of this kind of picture, that any sufficiently precocious undergrad could put this, multiply all the vertices together, integrate over the on-shell phase space of all the internal lines. In this case, you'll find that n hat delta equals 0, and so this thing is just some ordinary rational function. And a sufficiently precocious undergrad could take the definition of an on-shell function and convert that picture into this function. Now, I would never ask you to do that, and by Wednesday or by Thursday morning, you will know a much better way of getting from a picture like this to a formula like this. But I hope I've at least convinced you that these things are well defined. Okay. Now, one class of operations, you may or may not be sufficiently motivated to study this class of functions, but I hope you can see ahead and guess where things are going. It's a good idea to think about these functions. And so it's interesting to wonder with a class of functions you can start building up out of simpler things. And there's one operation which is useful to the point of completeness in planar case, in planar n equals 4, and it's not quite as universally valid, but it's still really, really useful for non-planar theories, is called adding a BCFW bridge. And here I'm definitely rewriting history, because this is, yeah, anyway. I'm going to call it a BCFW bridge for reasons that will become clear on the next slide. So the idea is that I take some graph like this. This is not necessarily an amplitude. This is just some diagram. And I'm going to add to the diagram this pair of vertices, and thereby define a new diagram. Now, what does n hat delta do? I've added 2 vertices, so I've added 4 times 2 delta functions, 8 new delta functions. Now, how about the internal lines? Here, I added 3 internal lines. There's a new line there, there, and there. So I have 3 times 3 new integrations, 9 new integrals, and 8 new delta functions. That means that I've dropped n hat delta by 1. So this new object is an integral over the old object, okay? With an unspecified contour at the moment. It's just some object. Okay. And it's easy to see that momentum conservation here, whatever the momentum is flowing through I, a hat is basically equal to a plus I, or maybe a minus I, and b hat is b plus I. And if you use momentum conservation of these vertices, this fixes lambda I and lambda tilde I up to a scale. So there's your new degree of freedom called alpha. And we can say that the shifted momenta, this just has the effect of shifting the momenta by this parameter alpha. And in the case of n equals 4, and I really mean just n equals 4 in the planar limit, this is the meaning of this picture is you can work out what this picture means in any theory, but in n equals 4 it has a very simple effect, which is that the new function is equal to the old function times d alpha over alpha. Couldn't possibly be simpler as a function of the hatted variables. So it just adds a simple little pole at alpha equals 0, which at least is about as nice as you could imagine, because when alpha equals 0, you recover the left-hand side. Okay. All right, now this kind of triviality has an immediate application that is extremely valuable that you probably have already seen. I just want to rephrase it in this graphical language, which is that you imagine you don't know what this endpoint amplitude is, but you imagine it's some sum of diagrams like this, and you attach a BCFW bridge to it. Now, of course, to get from the right-hand side to the left-hand side, you just delete alpha. You just go set alpha back equal to 0. So it's the residue at the origin of this shifted object. Okay. Now, but we all learned in complex kindergarten that the residue at the origin is equal to the sum of the residues away from the origin. And so, sure enough, instead of computing it as the residue at the origin, we can write it as a sum of the residues away from the origin, in which case every diagram was going to have a non-zero alpha there, so it's going to have this little bridge in every single term. And what are the poles away from the origin? They're all of the poles of this object, whatever it is. And if we're talking about the sum of Feynman diagrams, I'm going to kind of immediately generalize to talk about loop integrands, so sum of Feynman diagrams of any loop order. The poles always correspond to when a Feynman propagator goes on shell. Okay, and those can be divided into two different ways. Either the propagator that goes on shell breaks the diagram into two. If you cut it, then that's called a factorization channel. And if it doesn't break it into two, it breaks it into some lower loop Feynman diagram, which we're going to call a forward limit. Now, I wish I had more time to talk about this, but it's worth pointing out that while this statement, the fact that Feynman diagrams get partitioned into two groups like this, is a kind of a triviality of graph theory, an important thing that only works if you have some supersymmetry around is that the collection of all Feynman diagrams where this leg gets put on shell is equal to the the higher point lower loop amplitude in a theory with supersymmetry, and that's not true in, say, pure Yang-Mills. And I will leave it, I will leave it as a small exercise for you to convince yourself that in pure Yang-Mills, the sum of all Feynman diagrams with a cut topology with an extra pair of legs like this is not equal to the tree, say at one loop, that this is not equal to the tree amplitude with two extra legs in pure Yang-Mills. They differ by a certain class of diagrams, and this difference is not gauge invariant. So there's kind of a problem there. Nevertheless, maybe the integrand doesn't need to be gauge invariant. It usually isn't by Feynman diagrams. So maybe it doesn't matter. But in a theory with at least any amount of supersymmetry, you can prove this works. And if you know what the integrand means, we can prove this works anyway. So this has now been established for any planar theory with supersymmetry. Anyway, that's what the recursion relations are. Now, for the rest of for the remainder of this talk, I'm going to really focus in on the planar part. Well, actually, I might close with something about loops. But there's an interesting extra stratification that we can divide these diagrams into, which if I were talking about diagrams with arrows on them, if I was talking about gluonic amplitudes, I can talk about the number of minus helicities, which again, if I have this kind of arrow notation I had, which is it's the number of sources into the diagram. And that is counted as there's two sources per blue vertex. If you remember how I drew the arrows on the blue and white vertices, there's two sources per blue vertex, one per white vertex, and then -1 for each internal line. So there's a character called M which characterizes every graph that you can possibly draw, which is just given by this definition. Okay? And that's an interesting characteristic that will play a recurring role in the next few lectures. But anyway, there's a way to divide these graphs into certain M sectors. And across the bridge, I'll leave this as a bit of an exercise, that the M of the total is equal to M left plus M right -1. So that's, which is kind of maybe clear here. Anyway, it allows us to talk about doing the recursion for a fixed M. And in particular, if you remember that this Park-Taylor process, which is called the so-called MHV process, is M equals 2. And it turns out an amazing and fairly trivial application of this is that we immediately see the simplicity of Park-Taylor. I mean, this is just an absolutely incredible thing, that when you ask the recursion relations, what is the amplitude for two particles to create any number, all with the same helicity, that the answer is immediately one term. And to see this, you just need to know one little subtlety, which is if you try to go home and prove this yourself, you'll need to know this. So you always keep the bottom legs fixed. You have to choose. I could have actually chosen black to reverse these, but every single term in the recursion relation has a fixed n is on the blue vertex and a fixed white onto 1. And then you sum over all the things that satisfy this condition across the left and right. And for m equals 2, the sum of the left and the right has to be 3. So you can have an m equals 1 plus an m equals 2, or the vice versa. So there are two pictures that can contribute to the 4-particle amplitude. And we normally throw out the second one. Can anybody tell me why? Why is this one less important than that one? Well, if you solve the on-shell condition, the momentum conservation of these vertices tell you that all the lambdas that talk to this vertex have to be proportional to each other. And the same rule applies to this vertex. And that tells you that lambda of particle 1 has to be proportional to lambda of particle 2, which tells you that you're on a factorization channel. So I'm in my old age, I'm becoming more agnostic about throwing these things out. And the reason is because these are distributional pieces that I think could have implications for things like rational terms in QCD. Just because it's generally 0 doesn't mean that it doesn't contribute something. So anyway, we usually throw it out because relative to the first term, this term only contributes on a singular configuration. So we throw it out. And that argument immediately generalizes to all multiplicity, and you see that there's exactly one term that contributes to the endpoint m equals 2 amplitude, which is the lower point m equals 2 amplitude bridged with this 3-particle white vertex. So for 5 points, oh, by the way, and this is an important fact for the next lecture. Yeah?
Can I just stop you for a second? Can you go back to your previous slide where you had this equation m left plus m right is m plus 1?
Yeah.
So basically you're saying there are no graphs with m equals 0.
There are no graphs
Only
that.
one graph with m equals 1, which is the 3.1.
Yeah.
And for m equals 2, the right-hand side is 3.
Yeah.
There's only one way to make it up, right?
Yeah. Simple as that. Now, importantly, and this will play a huge role tomorrow, especially in the tutorial, is that an interesting fact about recursion is that it doesn't tell you which legs were 1 and n. You could have chosen anything you wanted. It didn't make any difference. And so instead of choosing legs 4 and 1, I could have chosen legs 4 and 3. And I would have gotten this. And it's not a sum over these diagrams. It's equal to, this is equal to the tree amplitude, and so is this. They're both equal to the tree. And that's an important diagrammatic relation. But we go to 5 particles, say, and we get one term in this recursion, which is the 4-particle m equals 2 with the 3-particle m equals 1. And now we pick 2 legs on this blob, and we blow it up. We put in one of these 2 pictures, and we get that. You'll start to notice that this picture is not very symmetric. The answer is symmetric. I'm not claiming that BCFW is giving you a symmetric form, although it kind of has to. And the diagram certainly is not symmetric, but it is important that it's giving you exactly one term. So if you ask for this 2 particles to 50 particles process, it's not 2 times 10 to the 83 Feynman diagrams, it's one term. And it starts looking like this. OK. And and this immediately generalizes to higher m in kind of the obvious way. And I realize that these pictures look a little scary or a little unfamiliar, but it's easy for you to compute that n hat delta for all these pictures is 0. These are rational functions. And I will leave it as an exercise, although honestly it'll be easier if you wait till after tomorrow to do the exercise, that this 2-loop weird thing in 5 points is equal to the Park-Taylor amplitude, and that this weird 3-loop thing is also equal to Park-Taylor for 6 particles. OK. Now, if we want to compute something that was actually known by this time, it gives very concise formulas for all the other things you could care about. So for example, for m equals 3 and k equals, and n equals 6, for 6 particles m equals 3, we have to divide up these partitions so that the sum is 4. And you can have 3 and 1, or you can have 2 and 2, or you can have 2 and 2. And then there are some other ones that also vanish. For example, a blue vertex on the right-hand side would vanish. So there are only these 3 pictures. And at every single time you see one of these vertices, you get to pick 2 legs and do the recursion. So you keep blowing it up. And you get some weird-looking formula for the 6-particle amplitude, which again, I hope you can appreciate this is less than 220 Feynman diagrams. And every building block is gauge invariant. And every building block has an infinite dimensional symmetry. There's a lot of nice things about this. OK. But I want to kind of end this talk on a couple just general observations about this. The first that it maybe, if you have seen BCF, the recursion relations you might not have fully appreciated, but I think are crucially important to this. The first is that there isn't a formula for any amplitude from BCFW. The recursion relation forces you to pick 2 legs, and it forces you to pick one of them to be black or blue and the other one to be white. And this choice gets repeated at every single stage of the recursion. You get to make this new choice every single time. And so there's a million different BCFW formulas. And varying which legs you pick to do the recursion can give you different formulas. So I will you can believe me that these three functions are all different functions. They're some weird functions of kinematics, but none of those three are equal to any of these three. So there's some, so that if you picked legs 6 and 1, you get these three functions for the answer. And if you picked legs 1 and 2, you get these three functions for the answer. And none of these three are equal to any of the other three. So you have some horrible 6-term rational function identity among rational superfunctions. It's kind of a horrible mess. And these kinds of identities proliferate at I forgot the number actually. It's something like for 8 particle n squared MHV, which is m equals 4, the number of terms that come out of recursion is always 20. But the number of distinct 20-term formulas you can generate is something like 25,000. Okay? And the statement that 20 terms is equal to 20 terms generates a vector space of identities of rank 105. It's some giant mess. So there isn't a formula for BCFW. There's a lot of formulas for BCFW. And this naturally led people to, oh, and another thing is that these diagrams look very different from each other. Although this kind of looks like the flip of that one, although not quite, because it's more like you have to flip and change colors. But it turns out that if you actually computed these, and it was noted in the original paper by B, C, and F, which is actually the precursor to the paper by Brito, Cacciazzo, Fang, and Witten, in which they derived it in terms of these pictures, by the way. So this is really like the BCF formula. Anyway, it was originally, it's noticed if you just compute these things that these are all basically the same function. That this function is equal to that function up to just a relabeling. So that although this formula looks kind of horrible and ugly in terms of these three weird looking graphs, that this function is the same as this one is the same as this one, and that just means you get to write one of these functions plus its rotation by 2 plus its rotation by 4, and that's the final answer. And so there are many more diagrams than there are functions you could possibly care about. That's one reason to not draw the diagrams, by the way. So it naturally leads you to wonder how to invariantly characterize the functions. We don't care about the diagram so much, we care about the functions. And in the next 2 lectures, I'm going to drive a bunch of ways of calculating these functions without using the standard definition of the product of all the trees integrated over the on-shell phase space, and thinking about how to do that efficiently, how to get thinking about how to characterize the diagrams and also how to compute the diagrams efficiently will lead us directly to a Grossmanian interpretation, which will have a lot of payoffs at the very end. So I think I'm going to stop there, and thank you very much.
Thanks a lot, Jake. Time for some questions.
I think you're all hungry for lunch.
Looks like that's the case.
Okay. Thank you.
We'll take a break for lunch. Come back with Utah.